starting with MR flow again. What was our flow, if you remember? Starting from input to input split, to record reader, record reader, mapper, combiner. This is well optional. The combiner is optional. I'll tell you where to use this combiner. Not always. We need in some condition to write a class for combiner. Otherwise, it's not required. Then after combiner, we will use partitioner. Then shuffle and sort. Then record writer. Then reducer. Then output. So this was our total MapReduce flow. Question comes from here only. They ask you what is the MapReduce flow and what is the individual use of this all. Okay, so if you do not understand, if you since we're saying that MapReduce is not actively being used in industry today, programmer have moved out successfully to Spark, and that is why your 60 to 70% weightage today is with Spark. There's no question coming from MapReduce, especially in the especially in this certification side. But as I said yesterday, whenever you talk about parallel processing first, just like we say any programming language father is C, we cannot ignore C whenever we talk about it. So similarly, when we talk about parallel processing, MapReduce we cannot forget. Okay, input to output. Input is already available in HDFS, and output is also available in HDFS. It will be available obviously when my whole flow is will be done successfully, and my command is able to read the input based on the logic they're able to process, transform, aggregate, and final output in HDFS. Okay, but from this point, input is split to reducer. Let me write down based on the numbers. So this is first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10. So first 10 is happening in HDFS, other 2 to 9 is happening in Node Manager. From here to here, all this is happening in Node Manager. Now, what is the input split? So when you copy your data to HDFS, when you copy your data to HDFS from local file system, what it does, it will split that data into number of blocks, right? So we'll take one example as 800 MB input file. So what is my task? My task is to process 800 MB, process 800 MB text data. Let's say the type of data is a text. And if you ask me what is the text data, this comes under unstructured category. Now, second point, immediately when they're asking me to process 800 MB text data, or precisely I will say not just process, write a MR program, write a MR program to process 800 MB text data. So they're asking ideally us to write a MR program. how many blocks it will create, guys, first. So block we know by default is 128. Divide 800 MB by 128. So I'll get 128 MB, 128 MB, 128 MB, 128 MB. This is in total 512 MB, right? Then 512 MB, if I take two more time, 128 MB and 128 MB, 36 total. So this is 512 MB plus 256. Let me quickly do a maths. I'm not using any calculator, but quick way, I think it's better to use calculator if you have any. 867. This is including of all this 6 block. And how many is pending out of 800? 32 MB is pending. 32 MB is last. So this many number of blocks I will get. Block 1, 2, 3, 4, 5, 6, and 7. So internally my data is stored in HDFS in this form: B1, B2, B3, B4, B5, B6, and B7. Now input part is done. What is input split? What is the input split? Second point. Block size is equal to number of input split. Number of block size is equal to number of input split. Obviously I can customize it also, but by default they take whatever the number of block you have. So if I customize my block, my input split will also be customized. We know that how to change the block size from 128 to any other number. Now, what is the difference? But we must be having some difference, because we cannot say exactly 100% they are similar. Block size you can see, right? We have seen that blk underscore some number. That was my block, how data is distributed internally. So block size is known as a physical division. And input split is known as a logical division. Okay, physical division and logical division. So you cannot see this. You cannot see input split. Input split will only come in a picture when you process any data using MapReduce job. Okay, so these are the logical division. So number of block size I have 7. How many input split I have? 7. There's a very interesting factor immediately after input split. Now input split is equal to number of map task. Input split is equal to number of map task. So how many tasks will be created? 7. T1, T2, T3, T4, T5, T6, T7. 7 tasks it will create. 7 tasks it will create of your 7 input split. What do we mean by task? This is a one job, because you have submitted only one jar file, right? To achieve this whole output, you're writing one MapReduce program, and using MapReduce program you have created a jar file, and using jar file then you have submitted using one command, which I already yesterday said you that what command you need to submit in a MapReduce to process that data. So how many number of tasks is there? Total number of tasks is 7. T1, T2, T3, T4, T5, T6, T7, which we can monitor also based on the task. Now obviously this all the tasks are processing in different machine. So let's say I have total 4 machine available. I have 4 machine available. So these are my machine. This is my machine number 1. I'll write it as node 1. Okay, this is my node 1, and node 1 is having running here node manager and data node. These are the slave. This is one. This is node manager 2, data node 2. This is second. Node manager 3, data node 3. This is third. And node manager 4, data node 4. This is fourth. We know how data distributes, right? Some data will go to all of this machine and your task will also be distributed like that based on the number of core available. So suppose there are 4 core, minimum we have 4 core available. Now to process this file, I only need 7 core free because I have total 7 tasks to process. Now out of this 16 core, suppose my cluster is having maximum 16 core. So out of 16 core, I just need 7 core to process this. Okay. This is what is your map task. Once the map task is done, and map task and reduce task is not working simultaneously, guys. Once the map is over, then your reducer starts or reduce task starts. So what is happening in a map phase, I'm calling as a map task. What will happen in a reducer phase, I will call it as a reduce task. Okay. So where this mapper, obviously they will generate some output. T1, once they T1, T2, T3 process, what they do, they acknowledge back to resource manager that we have completed our map phase. Now we are ready to start a reducer phase, right? That's what happens. So they submitted, this guy will submit to all of this machine based on their availability, and they start responding them back. So this is what is happening. This is communicating to all, they're communicating back to this. So first one was your submission, job submission, then task submission, and second one is your acknowledgement. So let me write, this is a task submission. This is a task submission. This is also a task submission. And this is a acknowledgement or response, acknowledgement and response, acknowledgement and response. So once they acknowledge back, where map task output will store. Map task output store, map task output will store in intermediate location. In intermediate location. What is the intermediate location? Intermediate is not HDFS. Intermediate is a local file system. And this is a temporary storage, guys. This is a temporary storage only till reducer is running. Once the reducer job is done, because reducer is taking output from where? Here. If you see my all the face, can you make one statement that all the variable, can you make one statement that all the variable are sorry, all the face. So these are my total 10 face. Every face output is next input for next phase. Every phase output is input for next phase. Because let's say I'm running this and some of the task fails or some of the step completely skips, my whole program will fail because they are interconnected. If any step is broken in between, my whole job will exit from the CPU or from the core. Okay, so every phase output is input for next phase. That's what we can get it from here. Resource manager is not getting any intermediate or any output. Resource manager, if you remember, master are only meant for monitoring purpose. Job is not done by master. Master are just monitoring. and taking their information. So this intermediate output will store in local file system of where? In this machine, in this data node. So once map task is done, it will store in this machine local file system. This will have some hard disk location for, because all this machine have a local LFS also and HDFS also, right? If I just type ls/ command, I can access local file system. If I type hdfs dfs minus lsn slash, I can access hdfs. So intermediate location means this map task output is not going in hdfs. This output is going in LFS, and this LFS is present in all the machine. This LFS is present in all the machine, right? So resource manager is only meant for monitoring purpose, just monitoring, just a master that how things are working. But uh, when I'm saying that this is HDFS, guys, HDFS is ultimately a part of LFS only, right? Earlier we had local file system, then we downloaded Hadoop, we built Java platform, we configured our activity, we configured SSH key, we write some property in XML file, we ran command to start the system, and this is how we built HDFS. But HDFS is a part of LFS only, right? It's which one is a superset here? LFS is a superset. If I talk in a math term, this is a superset and this is a subset. So HDFS is a part of LFS. LFS is not part of HDFS. Currently you have your Windows machine, Windows is LFS. Okay. Suppose you built HDFS. So you're taking some space from Windows and you're building HDFS. So let's say your total hard disk is 1 TB and you are assigning 100 GB. This is your total local file system hard disk and you are assigning HDFS for specifically 100 GB. So this is obviously 100 GB a part of this 1 TB only. Okay. So map task output will go to local file system, but remember, this is just a temporary output. Once your reducer job is done, this output will be deleted from here. This output will be deleted from the intermediate location. That is the only reason MapReduce is a slow business. MapReduce is not working as a Spark, because Spark, what does? Spark will keep this intermediate output in RAM. Remember this point, very important. When we say this is a in-memory processing and this is a disk computation. So in-memory processing means your intermediate output goes to cache, to RAM, for volatile purpose. When you are writing something in your actual hard disk, it's not volatile, it's non-volatile. When I say volatile and non-volatile, volatile is always a temporary, non-volatile is always a fixed file which you can refer anytime. Okay. So why Spark is faster? Just one reason. Spark will keep the intermediate output in their cache, in their RAM. Here, your intermediate output is going to hard disk. So reading from hard disk and reading from memory, disk operation is very costly. They take huge time to read back from reducer. But at the same time, if I'm reading from RAM, it's way faster than the disk computation operation. Okay, so that's one quick point here. When we say something is faster and something slower than that processing concept. So we know that I have already mentioned that disk computation point and in-memory processing point. But disk computation means, what do you understand? Every phase output. Suppose I'm having two phase or three phase. So every phase output is going to HDF to your hard disk. And if it is the in-memory processing, their intermediate result does not go to hard disk. Their intermediate result goes to RAM. The same thing happens with your Python programming also. That's why they are faster. That's why they're recommended for data science applications, because you're multiplying millions into trillions. So you play with the numbers like anything. You play with the data like petabyte, and petabyte is very 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 norm in data science applications and in big data, because they are dealing with the large internet companies, large e-commerce firms who deals with the petabytes data every day. So they're not supposed to keep their information in RDM image. Okay, so hopefully this point is clear, guys. These are all internal strategy, internal processing, that how things are designed for process the real time information and historical. But I cannot say MapReduce is completely replaced by Spark, because at times when I see there is a problem for RAM, there is a problem for processing, so immediately first thing comes that why don't we use a MapReduce? Do we have a compulsion that we need to use a Spark only? Can we replace a Spark thing with a MapReduce and use a MapReduce concept? Okay, so nothing is replacing any technology. What is main thing, that what application you're working with, it is purely based on the application. I won't say Spark is my favorite or MapReduce is my favorite, because a favorite can lead my whole program to the wrong direction. So I will take the application, I will read the problem statement, and based on the problem statement I'll take my decision. I can't say Spark is best or MapReduce is worst. Okay, it depends on the application. So we are here in MapReduce, and after map task, what is the next phase? So this map task is done, and after when I start a reducer part, they start reading from this map task and aggregate it. So let's take one example here and see this information. So suppose I have one input file. This is my input file, which I have already stored in HDFS. This is my input file, which I have already stored in HDFS. Okay, and this file size is precisely let's say 384 MB. And why I'm taking 384 MB? To get a 3 blocks, because if you multiply 128 into 3, you'll get this number, 384 MB. 384 is my input file, and this is a text data. Okay, suppose I have written something here. I'll write Python is easy, uh, Hadoop is best, Spark is fast. I've just written this 3 line, and I'm assuming that all this line are having 128 MB of size. Let's just say, okay, this all the line are having 128 MB size, so bigger files. Currently I'm not writing all the, because I cannot write 384 MB text information here. So taking this example, and this input is stored in HDFS. Okay, now you have created a jar file using your MapReduce program, and your jar file you have copied to server using WinSCP. So I'm assuming that you have input available in HDFS, and you have your jar file available in your local file system. Remember, sometime here we make a mistake. I'm not copying jar file to HDFS. My jar file is only available in my local file system of the server. You can make a quick note here that HDFS is only meant for data. HDFS is only designed for data. Never make a mistake that you're saying jar file you're also copying to HDFS. Jar file will be in local. Local means when you type lsn slash, you can see it. It won't be present in HDFS DFS minus lsn slash. Okay, so HDFS, because look, if you're copying jar file to HDFS, what is the use of copying jar file to HDFS? I'm not going to process the jar file. I'm going to process the data. And what I'm distributing, my jar file is hardly having 40 MB size, hardly, or maybe maximum if I'm writing so much logic, so maybe it is somewhere 1.3 GB. I'm not going to distribute this. I'm not processing jar file. I'm processing my data with the help of jar file. Okay, so jar file we keep in local. In WinSCP, you keep this jar file in your local file system. When we go and process this, actually, you'll see. So data is going to HDFS, and jar file is going to local file system. When I submit a jar file, and what was the command? Yesterday I ran this command. Let me rewrite again for you guys. How to submit a jar. So jar submission was this: Hadoop jar then jar file name. Here I'm just writing the name. Then class name. If there is a package, then package.class. If there is no package, then just a class. Then input. This is already available in HDFS, and output. Now input is there in a distributed format in all the machine across cluster, and output will be generated. Once my program is successfully done, this is yet to generate. This is not yet created. This is yet to create. So once program is done, then it will be created. I'll just give some name. So this name should not be present, guys, already. If this name is already present, suppose I'm writing this output as sample, and this sample folder is already available in HDFS, immediately my program will give me exception already exist. So make sure, and why you're getting already exist, if you're getting my point, this is in HDFS, this is also in HDFS. And what we have seen, the first point of HDFS works with write once, read multiple. If you have already present some directory, you will get this exception which says already exist. Okay, so when I submit this, this whole bunch of flow will start. This complete MapReduce flow will only start when you submit this jar file. And from where you are submitting this jar file, you're running this command from client machine, H node or client node. Okay. After submission, what is happening? Input split. And we have seen input split is equal to block size. So here, if my file size is 384 MB, how many blocks will it create? 3 block, 128 MB, 128 MB, and another 128 MB. So let's create an input split here. This is my input split number 1. This is 2. This is 3. Python is easy. Okay. This is my first input split. This is my, guys, I'm not doing one line by line. Again, remember, I'm considering this whole line as 128 MB. This line as a 128 MB because your input split will work like that only. Okay. Python is easy. In second line, I have Hadoop is best. So I've just written a random statement. Hadoop is best. And third, we have Spark is fast. If you understand one program, how this is working, you can design any program. You can create a graphical visual for them. This step is my second step, which is the input split. Okay. After input split, what will happen? Record reader. So there is one record reader utility. This utility will read this information one by one. And MapReduce is working with the concept of MR. MR is built with the concept of key value pair. Key value pair. We often call this is K comma V. K comma V means key and value. So this is one point for MapReduce, and second immediate point, that key can never be duplicate. This is universal. Key can never be duplicate. Okay, so value can be duplicate because my searching operation is working with the help of key only. If I want to search anything, I give key, and then key will go to that index wherever I have kept it based on the hash function. This is a concept of collection: hash table, hash functions, map. Okay, in Scala, when I design a program in Scala, we'll see what is the key and what is the value. So for now, key and value. Okay, it is always a key value pair, and key can never be duplicated. This is the internal concept of MapReduce. But here, Do we have any keywords multiple time? We do not have any keywords multiple time, but how they start reading it. So this whole line from zero index to whatever index is there till y, this whole line I call as a long writable. This whole line I call as a long writable. So in Hadoop, in MapReduce, what is a data type? In MR, what is a data types? If you simply think that from your database perspective and other programming, that I have long, I have integer, I have string, I have float, I have double, so their range is very less. This is a basic computer data types, basic programming language data types. MapReduce is saying that my one block itself is a big, my one block itself is 128 MB. You cannot handle that using long integer and this data type. So MapReduce has created their own data type. MapReduce is not following the traditional data type strategy. MapReduce says, okay, so we already have this existing data type. We already know the range that all they are varying between 602 65536, right? This all range of any data type is maximum. This is what, this is my ASCII value. This is my ASCII value. I'm going to bit of basic data types and computation, like how we design and how we define any variable to machine. Okay, so long, since long cannot work in MapReduce, what they do, what they did, they created one writable interface. They created one writable interface. The whole idea is to increase the range. The whole idea to do this, to write a writable interface, is to increase the range. So, and if you know byte size, this is 4 byte, this is 8 byte, this depends on the programming language, because a string follows many character. Somewhere they follow Unicode character, somewhere they follow ASCII character, somewhere they follow UTF-8 character. This is all encoding style. So it depends on the programming language. You're working with Scala, Java, Python. A string can be anything. Uh, I'll suppose, since we are in programming, I'll say this is a ASCII. This is ASCII type, which we have written there. So one characters. Float is again 4 byte. Double is again 8 byte. So top of my data type, what I'm doing, I'm writing one writable interface, and I'm taking this base data type, because these are my base data type. I'm taking this base data type and wrapping with this writable interface. So it's like I'm writing a wrapper classes. Okay, so I'm trying to write a wrapper classes for all this data type, and when I combine this long and writable, what it will create? It will create a new data type for MapReduce that we'll call long writable. And the whole idea why I'm doing this, to increase the range, because if I take a by default data type, which we have seen in traditional programming, this cannot work. You're not dealing with a gigabytes of data, guys. Always remember, you're working with the petabytes and terabytes. And obviously, if you're dealing with the gigabytes also, your one block is not 4 byte. Your one block itself is very big, which is 128 MB. And they do provide you custom operation. So if you want to increase your block size, you can increase it also. So if I say 128 MB is my one block size, how can I handle that in just long? That's the reason I'm creating long writable. Integer is int writable. So you just need to write it writable at last. This is a wrapper class. String, we do not call a string in MapReduce. We call them a text. So here it is changing. Float we call float. Float we call. It's a float writable. It's a float writable. Double writable. Double writable. Okay, so these are my data types which are presently available in MapReduce, and it is same in MapReduce 1 and MapReduce 2. Only couple of APIs are changing. So this is my long writable. This whole line, and how do I read them? So I read them based on the indexes. And so you know what is the index value starting from 0. 0. I'm reading for one line, then you'll understand how second line, third line will have their indexes. 0, 1, 2. So every character is having one index. 0, 1, 2, 3, 4, 5. Right? 0, 1, 2, 3, 4, 5. So 0 to 5 is the address. 0 to 5 is the address for Python. 0 to 5 is the address for Python, and that is known as a byte offset. So these are just terminologies, okay? These are just terminologies which we are referring here to nominate them, that if I'm saying 0 to 5 for Python, what do we call them? We call them a byte offset. If I read from 0 to last, the whole line is nothing but my long rank table. So 0 to 5 this, then this one is space, okay? You cannot ignore the space. Space is also counted as one index. So this is 6, then I is 7, 8, space again is 9, then this E will start from 10, 11, 12, 13. Now I can say 0 to 13. 0 to 13 is a whole address for first input split. This is my first input split. This is my second input split. This is my third input split. And we are saying they all are working parallelly. They all are working parallelly. So if they all are working parallelly, there is a chance that if I have 3 core available in single machine, they will work in single machine. If I have one core available in 3 different machine, they can go to 3 machines. It depends how many cores are free, which we have seen in resource manager. Okay. So 0 to 13 is all byte offset of first long writable, and similarly this will start from again. So if it is working in a different node, again it will start from 0 and similarly last. Again it will start from 0 and similarly last. Okay, so this is how your byte offset is designed. Now my question is, if you're saying that MapReduce is working with the concept of key and value pair. MapReduce is working with a key and value pair. So what if I have 2 times is written in the same? Let's say this Python is easy and there is one more is. In the same statement, there is one more is. So do we have any duplication? Because this is and this is exactly same. In fact, their case is also same, lowercase and lowercase, but their address will be different, guys, right? If you write here, their index value is not same. Their index value will be changed. So if I consider this is as a part of first input split, what will be address for this? 13, one space is 14, 15 and 16. I know my first is 7 and 8 index, and my last is 15 and 16 index. There is no chance of duplicacy because the index value, their byte offset itself is different. Okay, because this question can come when you say we did MapReduce input splitting. So what if you have same key multiple time in one input split? Same key is available in one input split, so their index value is different. This is how my input split is there. Now record reader is reading this input split one by one. There are different kind of record reader, and then they will pass it to, then they will submit it to task. Once this is done, immediately it will go to your core. This is my first core, this is my second core, this is my third core. Core means CPU, and that process is known as a mapper. Okay, what mapper does? Mapper will simply say, I will take all the key and provide them 1 1 1. I will initialize this all the key with 1 because obviously they're one time present. They're one time present. So it will say Python. Let me change the color here. It will say Python, comma 1 is, comma 1 easy, comma This will happen in my first core. First core will process this. Then second core will say Hadoop, comma 1 is, comma 1 best, comma 1. So they're iterating through individual individual key, and assigning them the value as by default 1, 1, and 1. Now, similarly, I had a question as earlier. You had is here. Just let's just say, okay, Python is easy is. You have this is in this whole line. So will you write is comma 2, or will you write is comma 1 two times? Will we write is comma 2 or is comma 1 then is comma 1? This thing we'll see when I will specifically tell you about this. Just hold for now. Currently I'm not talking about this combiner. Combiner is designed for specific use cases. So combiner we'll see with this example only. Aggregation is not happening in the mapper. Aggregation is not happening. This is point number 1, this is point number 2. Aggregation, because if I say is comma 2, which means I have aggregated. 2 means 1 plus 1. So I don't do this. I'm not doing this in mapper phase. Remember, if there are 10 times is also coming, I will write is comma 1, is comma 1, is comma 1 10 times. I will not aggregate it in the mapper phase. One thing to remember, mapper is not designed for aggregation. Aggregation will only happen in reducer, will only happen in reduce phase. Okay, so reducer means we call it a aggregation. Aiding the similar key if they are repeating. So first core, second core. What about third core? Same thing. Third core will also do. Spark, comma 1 is, comma 1 fast, comma 1. This is the output of third core. Okay. And where this output will store? This is a map task. Map task output goes to intermediate location in your hard disk, in your local file system hard disk, not in HDFS. After mapper, this is a very costly business. After mapper, so this is my one phase. When I had taken example of book reading, and I given all people 150 pages, I guess, right? Some equal number of pages to all people, and they did their job. They calculated by themselves, and then they talk to master that we have completed this task. So mapper is also doing the same thing. Once this is done, this part is done, then mapper, this node manager will immediately reply back or acknowledge back to resource manager that I have completed my first phase. I have completed my first phase. Similarly, this will also acknowledge, because they're not communicating to each other, right? We know that they do not know existence of each other. They're directly communicating to master. First phase, second phase, third phase. Third phase, because we have number of total 3 tasks. So this will acknowledge, this is acknowledgement, this is one acknowledgement, this is another acknowledgement. So all these 3 will reply back to resource manager we have completed. Now this is a resource manager job. This is a resource manager job to define the number of reduced tasks and where to run, in which machine to run. So this is what will happen now. This step is known as a shuffle and sort. Shuffle and sort. Very expensive operation. Why it is very expensive? Because they are trying to get the similar key in one place, and if it is not the same key, they're trying to keep in a different place. So how that key is sorted, that these are the same key. This Python, Hadoop, Spark, these are different keys. Who is doing this activity? Who is sorting the key? So key sorting is done by partitioner. Key sorting is done by partitioner. This is doing your key sorting. That's why we call it's a shuffle and sort phase. It's a shuffle and sort. Okay. So by default, they will handle this alphabetically. By default, they will handle it alphabetically from A to Z. Okay. So which is coming it first? We are getting first. Based on the spell, we are getting first. B is coming first, right? A, B, C, D. If I start from A to Z, B will come first. It will say best, comma 1. This is one key. Do we have any best here? There's just one best. Okay. Then second, uh, after B, we have E, right? A, B, C, D, E. E is there. So it will say, okay, easy, comma 1. Do we have easy anymore? No. Then third, H. Sorry, F will come first. Fast is also there. So fast, comma 1. So best, easy, and fast. These keys are sorted. These keys are sorted. And to do this, all the activity, your individual machines are communicating to each other. Your one machine is communicating to each other with the help of resource manager, because resource manager is only doing that activity. So resource manager says, okay, you can start exchanging this information. So it start exchanging node 1 information to node 2, node 2 information to node 1, node 2 information to node 3, node 4 information to node 2. This is all happening here. That's why I'm calling it's a shuffling stage, and shuffling stage is very expensive operation here. Okay. So I think there's a question. Sorting is happening based on the key, Jatinder, that is a partitioner step. So after sorting happens, then shuffling happens. So sorting means they're deciding the number of keys available in your in your input file. So how many keys are there? If I count it, 1 2 3 4 5 6 7 8 9. Total number of keys are 9, right? This is, I know, in my mapper phase. Now it will say how many keys are same. How many keys are same? So we say is. This is only the same key. Rest everything is a different. So that job is done by resource manager. That job is done by sorry, my mistake. My bad. This job is done by partitioner. So partitioner is helping you to sort out the key, and once keys are sorted, once this key is sorted by partitioner, then they are shuffling it. So first sorting phase will happen, then they start doing it uh, then they start doing it shuffling. Okay, so sorting and shuffling is a step. So best comma 1, easy comma 1, fast comma 1. Okay, uh, what is the next after F? We have Hadoop comma 1. Hadoop comma 1. Hadoop comma 1. What else after? So I think this is sorted, this sorted, then we need P. Sorry, I after Hadoop I will come, then P, then S. Now the interesting part here, this is same, this is same, this is same. All these three keys are same. So it will say is comma 1, is comma 1, is comma 1. All three things will be, these are same keys. So they will go and store in a same disk to process. This is happening in a same one machine. Okay, this is in one core. This is happening in one core. Maybe these are happening in different core, possible, but this must be happening in one core, because this is all the keys are same here. Okay, and then rest are same. After I have Python comma 1, Then after Python comma 1, I have a Spark comma 1. And this is how it is happening. Best, easy is coming from here. Then I think there's a question. Let me just complete this part. I'll come to the question in just five minutes. Okay. Let me complete this part first. Hadoop is coming from here. Is coming. Is coming. Is again coming. Python is coming from here. Then last is a Spark. Spark is coming from here. And guys, remember, if I type is this and if I type is this, I is a uppercase here, I is a lowercase. They are not same. They are different. They're not same. They're different because of case. Okay. So if you check the address also in memory location, their address is different. They're not same because uppercase has a different ASCII and lowercase has a different ASCII. Their ASCII is different. Hence it will be different. Okay. Their index value itself is different. So any key which is having lowercase and uppercase, they're different. Do not consider them as the same. This is my shuffling and sorting phase. And after shuffling and sorting, the next step is my reducer stage. Next stage my reducer. In reducer, I will say, okay. So in reducer, I'll say best is there, okay, one time. So combine them. Say best comma 1, easy comma 1, fast comma 1. This is the stage where aggregation will happen. This is the stage where aggregation will happen. Easy comma what? 1 plus 1 plus 1. 1 plus 1 plus 1. Guess what? 3. Python comma 1 and Spark comma 1. That's what reducer does. Reducer in short, aggregation. Now my final output will be created. This is the final OPT. Final OPT. In one file or in two file, it based on the number of reduced tasks. If I've said that this will have two reduced tasks, it will create a two file inside a folder. If I say just one reduced task, this whole file will be stored in one file. This whole data will be stored in one file. So since I have left less space, I will just write the first. So I'll just write the first this one. Let me write this output in the next. I'll write it here. I don't have a space left in this side, so I'll write it here. My final OPT will look like this. In a file, it will store best, comma 1, easy, comma 1, fast, comma 1, Hadoop, comma 1, is, comma 3, Python, comma 1, and Spark, comma 1. This is my final OPT, final output. This was present in HDFS. This will also go and store file in HDFS with some name. Whatever folder name I will define for this output. For this output, whatever name I define, it will go inside this folder and we can see the output. Okay. Input is in HDFS, output is in HDFS. This whole step is happening in node manager, node manager, node manager, node manager, and that's it, node manager. Okay. One thing I did not discuss about combiner. Combiner we did not discuss. Combiner is short part, I will tell you here. So we have seen Python 1 is 1, easy 1, right? Now here when you are transferring your data, it's going one by one. So when it is going one by one, your IOPS time is very high. Your network traffic time, your transfer rate. Do you understand your transfer rate? Your transfer rate is very high because you are sending one packet at a time. One packet using protocol called ICMP, Internet Control Message Protocol. Okay, so one packet is going. That's why the communication will be very high, and this step is taking time. Uh, Sometime when we're running MapReduce job, if I talk in my experience, some of the jobs are running since last 48 hours also due to the core unavailability. So if core is not available, it runs days and days. And we go there and check the log file, and we just ensure that if I have seen 2 hours ago that progress state was 70%, and I check after 2 hours again, then I see progress state has raised to 78%, which means I ensure that okay, this is working. Slow is there because due to number of core is unavailable. That's why they're taking time. So what is a combiner? What is a combiner? Just last point, then I'll come to your question. Just last point. Uh, because all of this point I think is clear. Input split, we know it is equal to this is logical division. Record reader, it will read all the data. So record reader, who is doing this task? Long writable byte offset, this is reading by record reader. This information is given by record reader, it is reading one by one. Okay, then mapper. Mapper is map task. So this is processing based on the core one by one, taking your keys, assigning the value. Partitioner, we know based on the key it will sort and shuffle it, and after shuffling, it will start writing to using record writer to reducer, and reducer will write that information, aggregate them, and keep the final copy in your output file. Combiner, last point. Then we'll see question. Combiner. Suppose in this core I have Python, 1 is 1, easy, 1, and I'll take one more time is 1. I'll take one more is 1. Okay, because I have is here. I'm just assuming this is one more is, and because there is one more is. Okay, so if I'm combining it this level, because if I'm sending this key one by one, how many times I'm communicating? 4 times. One for this, second, third, fourth. 4 times I'm sending my packet. But can I do one thing in this stage itself, which is a combined stage? Can I say Python, 1 is 2 and easy, 1. If I do this aggregation, guys, if I do this aggregation in my mapper phase, then this is known as a combiner stage. And combiner stage is helping you to increase your performance, because now you're not sending is 1 at one time and is 1 at second time. You're sending this whole packet at one shot. So when you send this whole packet at one shot, you have increased your total performance 1x time. And suppose likewise you have 100 keys repetitive in this mapper, so you can combine it local level, and then you can do shorting. So your total communication will definitely improvise and increase. This is nothing but a stage of combiner. So if you are having similar keys repeating many times, okay, similar keys repeating in many times in the same core, so it's better to aggregate them. It's better to aggregate them there itself, and then after aggregation based on the key, sort them and shuffle in a reducer. So combiner is also known as, one point to remember, combiner is also known as mini reducer. Combiner is also known as mini reducer. Very important point. At times this work like a magic. Suppose my one program is taking 3 hours. Actually, I've used this combiner in my transactions monitoring operations. So when we had the many transaction from the same person, right? If one person is doing 1 month 5,000 time transaction, let's say he or she is working with a credit account. a current account, not a saving account, right? So same transaction is happening multiple time. I'm talking about the real time application. So there, if same person is doing multiple time transaction, the key will be same, but their transaction time is different. So I want to aggregate the key, right? That's what I'm doing in combiner phase. So combiner will aggregate at local level to increase their performance. Combiner is not required every time. This is optional. So based on your input file, you decide, developer will decide whether to take the combiner stage or not. So if I take, it's okay. If I do not take, my program will never fail. But just the case that if I'm having same key multiple time, and if there is a small area also to increase your performance, it's better or best recommendation that use the combiner. This is the whole strategy of MapReduce, guys. This is how it works. Currently, I'm talking about one simple text data. Whatever data is, you talk about um, you talk about log file, you talk about audio file, video file, image data, anything, any information does work like the same. Their flow is exactly same. After input, it will happen input is split, then mapper, then sublink, then reducer, then last is out. Let's say question now. So keys are duplicate and keys should be unique. Sorry, keys are duplicate. How can you say keys are duplicate? Because all the keys are having different indexes. This index, and suppose I'm having one more is here in my file. So this is and this is different indexing, right? This is will not have the same index as this. If I start reading their byte offset, it is 0, 1, 2, 3, 4, 5. It is 7, 8. This is 10, 11, 12, 13, 14, and this is 15 and 16. How come they're same? They're different. Internally, their byte offset is different. Okay. Anybody, any more question, guys? So this is, I know it cannot be just done in one one session, uh, because this is little tricky, and we'll have to go to we will have to read this their definition. So I'll do one thing. I have a file. I have a comic uh, comic created for this. I'll share that comic with you guys. Please go through and read that. So I have tried to simplify them in a best term and in easy term. Okay. So this needs multiple time reading. I'm frankly saying you this cannot be done in just one session. You cannot, if you're thinking that this is very crucial and very complex and very uh, uh, very difficult to understand the whole flow. So yes, it will take time. It will take time to digest this and come out with the best flow that this is what I can design for processing the output. Okay, so read this file again and again. Try to understand input split mapper and first focus on the whole flow. Forget about what I discussed in previous class. Focus because I think processing part is clear to all of you that how we are distributing the data across node, how core part is handled. But this is what is happening internally. This is what is happening internally. So read this again and again. At least try reading 3 4 times the same information and try to digest this. Then we'll see with some other operation also that how things can work it best way. Multi-node configuration video. Okay, multi-node configuration video I've not shared. I guess I'll share that. I think it's I've converted. So yesterday video is also converted. I'll share everyday videos now. So I think I have shared two videos with you guys. MapReduce 1, MapReduce 2 part. Couple of other videos I have converted. So I'll share that video today. Start watching it, and I think you guys have book fourth edition book I shared with you, right? Definitive Guide. Fourth edition of Definitive Guide book is with you. Okay, so please read that book. Read that book, understand the terminology, and uh, understand the flow. Look, these terms are we can remember these terms, right? But how this concept is going, how this they are processing, if one is failing, if second is failing, because this is what happening when I say task. This is my one task, T1 of map task. This is my one task of reduce task. uh, okay, so there I'm working with a task, and you're seeing this block design. I've created different block, like Python is easy in one block, and similarly Hadoop is based in second block. This is nothing but they're processing in task, and we know that one task is processing in one core. So this is about one core. This is about uh, here I can define that two core, two task or one task. So if I say one task, it will go only in one core. If I say two task, it will go to two core. So uh, always your number of mapper is more, number of reducer is less. You're not giving the same number of mapper and same number of reducer, and there are multiple things coming then. In next class we'll cover tomorrow, next topic will cover tomorrow, that if I do not have mapper, if I have one mapper, if I have reducer, so this is one whole flow. But yeah, if I have just one mapper created, if there is no reducer, if there is a zero mapper, if there is one reducer, so what will happen? Such scenarios we'll cover tomorrow.